18 minutes. That's all the ground gave the people of Shanghai County before it ruptured a second time. First, a magnitude 5.7. Then, 18 minutes later, a 5.8. And right now, seismologists around the world are asking the same question you're probably asking too. Why do these paired earthquakes keep showing up, one right after another, in such tight windows of time, in completely different corners of the planet? We saw it recently in Venezuela. 2 strong quakes just 39 seconds apart, both registering higher on the magnitude scale than what we're looking at here. Now here in China, we have a 5.7 followed by a 5.8, both striking at nearly the same depth, both breaking the same handful of kilometers of rock. And here's what almost nobody is saying out loud right now. This exact location has already produced a destructive magnitude 6.6 earthquake once before. So the real question isn't just what happened this morning, it's whether this is the opening act of something bigger and what we should actually expect if it is. In the next few minutes, I'm going to walk you through 3 things. First, what the beach ball fault diagram of the 5.7 tells us about how the ground actually moved beneath those 18 minutes of silence. Second, why calling that 5.7 a foreshock is technically accurate, and at the same time dangerously misleading, because of everything that label quietly assumes about events we can't actually confirm yet. And third, the 5 specific signals seismologists are watching right now in real time that would tell us this sequence is turning into something far more serious than a couple of moderate shocks. Stick around for that last part especially. It's the one that matters most, and it's the one seismologists themselves are keeping their eyes glued to as new data comes in hour by hour. So let's start with what actually happened, using the raw numbers coming out of the Chinese seismic network. The first quake, magnitude 5.7, 10 kilometers deep, roughly 6 miles down, hitting at 11:16 in the morning, Beijing local time. Just 18 minutes later, a second rupture. Magnitude 5.8, at the same depth striking within a few kilometers of the first. 2 earthquakes that close together in space and time at that same depth are not 2 separate, unrelated events that simply happen to share a morning. That's one fault system rupturing twice within the space of less than 20 minutes. And at 10 kilometers deep, this is shallow. Genuinely shallow, and that's a fact we can be confident about even before all the finer details settle into place. It matters more than the raw magnitude number does, because a shallow 5.8 shakes the surface far harder than a much larger earthquake sitting deep underground ever could. There's almost nothing standing between the rupture itself and the villages built directly on top of it. No thick cushion of rock to absorb and soften the shaking before it reaches the surface where people actually live. So was that first 5.7 a foreshock? For now, technically, the answer is yes. But the definition behind that word is far simpler and blunter than most people realize. If a bigger earthquake happens nearby afterward, then everything that came before it automatically gets relabeled a foreshock, whether or not it was ever building toward that bigger event on purpose. The 5.8 was larger. It struck close by. So the 5.7 gets reclassified retroactively as the foreshock. That's just how the terminology works. But here's the problem, and it's a real one. The difference between a 5.7 and a 5.8 sounds tiny on paper, just 1/10 of a point, but it actually represents a meaningful jump in released energy. At the same time, that gap sits comfortably within the normal margin of uncertainty between different seismic monitoring agencies, who routinely disagree with each other by more than that on the exact same event. So confidently declaring one shock the foreshock and the other the main shock is really drawing a sharp line that the underlying data doesn't fully support yet. The more honest, more careful description is that we're looking at an earthquake doublet, 2 roughly equal ruptures, sitting side by side at essentially the same location, minutes apart. And that brings us to the question everyone actually wants answered. Are both of these shocks just foreshocks to something even bigger still coming? Nobody can tell you that with any certainty. Not me, not the USGS, not the Chinese seismic network, not anyone. A foreshock is only ever formally identified after the larger earthquake has already struck. That's not scientists dodging the question or hedging their bets unnecessarily. That's simply the physics and the logic of how earthquake sequences work. You can't label the beginning of a story until you've read the ending. What we do have, though, is a global statistical baseline, and it's genuinely useful context. Roughly 5% of earthquakes worldwide are followed by a larger one nearby within a week of the first. We just watched exactly that happen in Venezuela, where the second, larger shock arrived only 39 seconds after the first one. 5% is a global average, not a specific forecast built for this exact spot in China, but it's also far from zero, and it's precisely why no serious seismologist is willing to close the book on this sequence just yet. Now, let's talk about what the rock itself actually did during that first 5.7 rupture, because the data here is unusually clean and worth walking through. The 5.7 gave scientists a very clear read on how the fault moved. what's technically called a beach ball solution, a diagram that shows the direction and style of slip along the fault plane. This one came back at 96% double couple, which in plain language means this was an ordinary tectonic slip event. Rock sliding directly past rock. Nothing unusual happening beneath the surface. No magma movement, no volcanic trigger, nothing exotic or mysterious lurking underneath. That matters, because whenever a sequence like this hits the news, exotic explanations start flooding social media within the hour, and the actual seismic data closes that door immediately and decisively. The motion itself was overwhelmingly horizontal. A strike-slip earthquake, meaning the two sides of the fault ground sideways past each other with only the faintest whisper of vertical movement layered underneath that horizontal slip. The compression ran roughly northeast to southwest, while the extension ran roughly northwest to southeast. And that's exactly the pattern you'd expect to see in this particular part of the world, where the Indian tectonic plate is still driving steadily north into the Eurasian plate, inch by inch, year after year, in a process that's been unfolding for tens of millions of years. That immense collision has to release its energy somewhere. And since the crust simply can't keep piling upward forever, it goes sideways instead. This earthquake is essentially that colossal, slow-motion continental collision playing out in miniature, compressed into a matter of seconds, directly underneath a handful of mountain villages that had no warning it was coming. So which specific fault actually broke here? This is where the easy, obvious answer shows up first, and where that easy answer is probably wrong. Most of the coverage on this event will simply say it was the East Kunlun Fault, and move on, because that's the famous, well-documented structure, the one with its own detailed research history and its own place in the textbooks. But I don't think that's actually the answer here. These quakes struck right around 99.5 degrees east, a specific point where the main left lateral Kunlun fault system makes a significant bend, handing off from one fault segment to the next like a baton in a relay race. Bends like this are exactly where fault systems tend to get messy and complicated. Instead of one single clean line running across the map, you get the main east-west trace running alongside several parallel splays, all of it crossed by smaller north-south and north-northeast oriented structures, cutting straight across the whole system. I think one of those smaller cross-cutting faults, not the headline Kunlun trace that gets all the attention in the news coverage, is what actually ruptured here today. This isn't just a minor technicality buried in the geology. We already know from other regions that these smaller branch faults can trigger movement on a much larger, locked fault segment sitting nearby, transferring stress across the junction where they meet. It's part of the standard playbook seismologists study closely along California's San Andreas fault system as well. So if this cross-cutting structure really is what ruptured, the important follow-up question becomes whether it's now quietly loading additional stress onto the larger fault it intersects. The relocated aftershock data expected over the coming days should help confirm this theory or rule it out entirely once the smaller aftershocks get mapped with more precision. Here's why I'm raising this possibility now rather than waiting for that confirmation, and it comes down to what happened in exactly the same spot 26 years ago. On September 12th, 2000 to be precise, a magnitude 6.6 earthquake struck Shanghai at roughly 35.3 degrees north, 99.5 degrees east, a location only about 8 kilometers or 5 miles from where today's double earthquake struck. Given the normal location uncertainty involved in mapping earthquake epicenters, that's effectively the same source region we're dealing with right now. And interestingly, the research into that magnitude 6.6 event from 2000 also didn't place its rupture on the main east-west Kunlun trace. It pointed instead to a north-northeast oriented fault running straight through this same epicentral region we're discussing today. Same spot, same orientation. We're almost certainly watching the very same structure that produced that 6.6 back in 2000, rupturing again right now, only smaller, at least for the moment. The damage from that 2000 quake is worth remembering in careful detail, because it tells us exactly what this particular stretch of ground is capable of doing to the people living on top of it. 5 people were injured in Wengquang Township alone. 75. Houses collapsed outright. 948 more houses were seriously damaged, and at least 3 magnitude 5 aftershocks followed shortly afterward. Compounding the destruction even further, read those numbers again, slowly. 75 homes completely gone. Nearly 1,000 more left standing, but structurally broken. Those figures aren't really a statistic about earthquake magnitude. They're a statistic about how the buildings in this particular region respond to shaking. Older masonry and adobe construction, combined with a shallow rupture close to the surface, combined again with steep mountain terrain that tends to amplify shaking even further. That exact combination of risk factors is still sitting here today, completely unchanged since the year 2000. This is not some quiet, forgotten corner of the map suddenly misbehaving out of nowhere. This is a source region with a demonstrated, well-documented ability to produce a magnitude 6.6 earthquake. And right now, that same region is waking back up with a double earthquake of its own. Now, you might be remembering another significant earthquake from just a few weeks ago, and you'd be right to bring it up. On June 16th, a magnitude 6.3 struck near Hexie, with strong aftershocks that included several magnitude 5.2 events. But that earthquake occurred 446 kilometers, about 277 miles, northwest of today's epicenter, and it ruptured on a predominantly reverse fault, which is a completely different mechanism from what we're seeing here. In that case, the ground moved up and over rather than sideways. Both earthquakes are, in a broad sense, children of the same massive continental collision reshaping this entire region of the world, but there's no solid evidence linking these two specific events directly to one another. Don't let anyone tell you that the June earthquake somehow caused or triggered what happened in July across that kind of distance. The data simply doesn't support that connection, no matter how tempting it might be to draw a straight line between two dramatic headlines. So what can we realistically expect from here? The most likely outcome, based on how these sequences typically behave, is a steady stream of smaller aftershocks that gradually taper off over the coming days and weeks. But because the rupture sits at only 10 to 12 kilometers deep, roughly 5 to 7 miles, even magnitude 3 and magnitude 4 aftershocks will be felt strongly on the surface, simply because there's so little rock between the source and the people standing above it. Given the structure of this fault system and the fact that we're dealing with two nearly equal ruptures rather than one clean, decisive break, another shock somewhere in the 5.0 to 5.8 range is genuinely plausible. Two near equal ruptures like this often mean the fault is stepping between adjacent locked patches of stress rather than releasing everything cleanly in a single event. A full magnitude 6 earthquake is possible, though somewhat less likely. But we know this fault is physically capable of producing one because the year 2000 already proved exactly that. A magnitude 7 event is possible in theory, but it would require rupture along a much longer stretch of the broader Kunlun fault system than what we're currently seeing, a system that has, in fact, produced magnitude 7 plus earthquakes before, including one roughly 7.5 in magnitude to the west of here back in 1937. Two magnitude 5 earthquakes alone don't prove that a magnitude 7 is currently loading somewhere beneath the surface, but it absolutely can't be ruled out either. This particular region sits deep inland, so tsunamis aren't a concern here at all. That's at least one small piece of good news in an otherwise tense situation. But the real risks on the ground are rockfall and landslides on mountain slopes that have already been loosened and destabilized by these first two shocks, even without any further seismic activity. Add potential road damage on top of that, and you're looking at access being cut off to exactly the villages that would need outside help the most if conditions worsen. From here, a serious concern in terrain this remote and mountainous. And then there are the older masonry and adobe buildings scattered throughout the region, many of them built decades ago without modern seismic reinforcement, structures that could fail completely if another strong jolt arrives, even one no larger than what has already struck. It doesn't take a bigger earthquake to bring down a building that's already been weakened once by the shocks that came before it. Sometimes the second or third hit is all it takes. So here are the 5 specific signals I'd personally be watching closely, the ones that would raise my concern level significantly if any of them start to appear over the coming days and weeks. Number 1, magnitude. 5 class earthquakes start migrating along a clear, identifiable line rather than staying tightly clustered in one small area the way they are right now. That kind of migration usually points to stress spreading progressively along a longer stretch of fault rather than staying contained. Number 2, the overall activity spreads out across tens of miles instead of remaining concentrated in the same small region, a sign that more of the surrounding fault network is becoming involved. Number 3, if a later earthquake's fault mechanism closely matches the mechanism of the first 5.7, that would confirm repeated slip happening on the exact same underlying structure, rather than several unrelated faults reacting independently. Number 4, aftershocks begin aligning themselves along the longer main east-west Kunlun fault trace, rather than staying confined to this smaller cross-cuttings structure we've been discussing. And number 5, Chinese monitoring agencies start reporting an acceleration in aftershock activity instead of the normal, expected gradual decline that most sequences follow in the days after the initial rupture. If any single one of those 5 signals shows up in the coming days, the entire conversation around this earthquake sequence changes, and the risk assessment for this region shifts along with it. For now, though, this remains a doublet worth watching closely and carefully, not a confirmed warning that something larger is already building underground. Nobody, not me, not the Chinese Seismic Network, not the USGS, can promise you with any certainty which way this situation goes next. What we can do, all of us, is keep watching the incoming data closely keep applying these same 5 checkpoints as new information arrives, and update you the moment any of them start to shift in a concerning direction. That's exactly what I intend to do over the coming days. I'll be tracking this aftershock sequence closely as it develops, and if this region starts showing any of those warning signs I just walked you through, you'll hear about it here first, before it becomes bigger news elsewhere. In the meantime, if you want to understand more about how seismologists actually read signals like these in real time, how a handful of numbers on a seismograph readout eventually turn into either a genuine warning or a reassuring all clear, stick around, because there's another video right here that breaks that whole process down in even more depth. It's strange, it's genuinely fascinating, and I think you're going to enjoy it. I'll see you there in just a second.